we're going to have some quantity R that we want to calculate. We're going to have an approximation method of some type, A of h, which is based on some parameter h. For example, h might be the delta x of our integral approximation method. R might be the actual true value of the integral, and A of h might be the right integral approximation. Or possibly some other approximation of some quantity that we're interested in. We'll write the difference between the approximation and the true desired value to be E of h. E is for error, and obviously it will depend on the size of the h. This E of h, generally speaking, is an unknown function to us. In an act of blatant optimism, I'm going to assume that I can expand E of h in a power series in terms of h in the same way that you did in the second semester of calculus. The coefficients alpha 1, alpha 2, and so on are not known to me, so at first glance it seems as though this wouldn't be of any great use. That turns out to be wrong. I can imagine evaluating the spacing for some value h, and then also evaluating the approximation using half of that spacing, or a quarter of that spacing, or if I wanted 1/8 or 1/16, and so on. If I simplify the algebra from the preceding formulas, I get these three formulas. H is first replaced with h over 2, then h over 4 for the last formula. There's an interesting observation to be made. If I take the second equation and multiply it by 2, the h to the first power terms will be the same. If I take the third equation, multiply it by 2, the h to the first power term is the same as in the second equation. If I carry this idea out, I will get things that start off with an h squared instead of an h, which hopefully would give me a more accurate estimate. This is true even though I don't know what the alpha numbers are. So I'll call my approximation based on h, little a, b will be the approximation based on h over 2, and c will be the approximation based on h over 4. 1 prime, I'm going to calculate d, which is 2 times the approximation based on h over 2, minus the approximation based on h, and 2 prime, e, will be 2 times the approximation based on h over 4, minus the approximation based on h over 2. We can work the algebra out for d and simplify. Likewise, we can work the algebra out for e and simplify. This is going to form the basis of a conjecture. I'll start off with numbers A, B, and C, or even D. These are approximations based on h over 2, h over 4, and h over a. We know how to combine such approximations to get approximations that are h squared at the beginning of their error term. We've also just seen how to combine two order h squared approximations in order to get an order h cubed one. I conjecture that this pattern maintains itself. I can combine I and h in a similar way using not 2 to the first or 2 squared, but 2 cubed instead to get something that's even more accurate. I'll call this approximation J. In a later video, we will prove that this conjecture is right. If I had more rows and columns, I would continue this pattern. Each new number is 2 to a power multiplied by the number immediately to the left minus a number immediately above, the whole thing divided by 1 less than a power of 2. For now, this is a guess. It's based on the pattern that we're seeing. What does this have to do with anything, the person might be thinking? Do you remember those really bad approximations to a certain integral? The ones that weren't very accurate, yet were based on spacings involving 1 subdivision, 2, 4, and 8. In my notes here, it says, insert evil cackle. We will see. Seriously, I hope everyone's having a good day, and I'll talk to you again soon.